You'll be able to get a copy of it. I want to thank Michael McClellan. He's been organizing these lunch and learns. We've done one almost every day to help all our customers during this time where you're stuck in your house and you need some sanity. So, hey, Chris. So I hope you find this quite interesting. Today I'm going to talk about using the right CTs and PTs for your application. It's a subject that's near and dear to my heart because I've run across too many applications where specifically manufacturers don't give you a nice enough quality CT, and it causes all kind of issues for us. I also gave this presentation an alternate name. Was now I know what I do not know about CTs and PTs. Half the battle for us as engineers is finding out how to, if we find out what we don't know, then we can find out what we need to know. So, we don't need to know all the answers, just where to go find them. We're representatives for GE ITI. Here's just a smattering of all the different types of CTs and PTs and current transformers that they make. So there's a huge selection, and what I found is there's probably about 10 different CTs you could use for the same application. Here's my agenda for today. I'm going to talk about current transformers, voltage transformers, some information you need to specify them. I've got a bunch of about 7 or 8 take-home rules, and then applications where you use them if I've got time to get into that. So the first question is, what's an instrument transformer? And this applies to both a CT or a PT. The first thing we do is we use it for circuit isolation. So I can isolate voltages with it. I can reduce voltage and currents to reasonable working levels. If I've got a 3000 to 5 CT, I don't want 3000 amps going through my GE multi-lin meter. I only want 5 amps, and we can have universal relays because of that. And then we can do phasor combinations for measuring and summing and do all kind of other cute tricks if we need to. There's 2 basic CTs that you'll run across. The most popular is probably a window CT. So we put the wire through the window, or occasionally on 5 kV, you'll actually see a bar type CT. So they just connect to each side, and basically this has the equivalent of a donut inside that CT. So let's talk about what a CT is. A CT physically is very simple. All you have is an iron coil and some wire. And then we have a piece of conductor goes through the center, and then there's wrappings around the secondary, and all that ratio determines how many wires are wrapped around, determines our ratio. If you physically look at it, this is what you've got. All I've got is this iron core in here, and then we just wrap the windings around it. And if you notice that you see here, this is kind of a goldish color. Does anybody know what that is? If you do, just chat me. If you think you know why I'm not, is that bare copper there? Anybody got a chat answer what that is? Guess not. I'm going to ask a lot of questions. If you want to just chat the answer, I can see that at the same time. That's actually insulation on that copper wire. One thing you need to be aware of is BIL. Their standard BIL is basically impulse levels. So that's lightning and surge of what it can take. So a 600 volt CT can take a 10 kV BIL level, just to let you know. And this is kind of why you'll end up seeing, when I get into large CTs and PTs, why they end up, looking like this instead of like this at high voltages. It's because I need the higher BIL levels so it doesn't blow up on you. Now let's talk about the ratio. Enamel wiring. Very good, Marshall. What you've got is, you've got a ratio here. So if I have 100 amps go through this because of those windings going around the secondary, and I have 5 amps, people will call this either a 100 to 5 CT, or sometimes it gets kind of confusing because they'll say my ratio is 20 to 1. Well, in the US, what's our standard secondary? Somebody want to give me the answer to that for CTs? 5 amps. Very good, Mark. In Europe, what's the standard they tend to use? Anybody knows that? 1 amp. Very good. So if somebody just tells me it's a 20 to 1, I need to go find out, do they want a 5 amp secondary or a 1 amp secondary? In the US, 99% of the time, you're going to see a 5 amp secondary. So 100 to 5, which is a 20 to 1 ratio, is the same thing. Now, let me ask you this. If I end up running, this is a 200 to 5 CT. If I end up running this wire through there twice, what does that make it? Is it still a 200 to 5 CT? Somebody tell me what the answer is. Y'all are good engineers. What's my ratio going to end up being? Very good, Chris. It's going to be 100 to 5. So if you have a CT that's too big, or you need a higher class CT, that's a good trick to do to actually figure out a way to get around and change your ratio. Excellent. So I could use a 200 to 5 with 1, 100 to 5 would be 2, 55 would be with 4. Okay? And here's some different configurations. A lot of times in CTs, you'll hear what's called a single ratio. So that's 1 primary, 1 secondary. Sometimes we have a dual ratio. So here's the case of I've got a 200 or a 400 to 5. So if I've got all the windings, it's going to be the 400 to 5, and half the windings would be the 200 to 5. And then here's multi-ratio. So we get into a lot of different configurations of CTs where you may have multiple secondaries with 1 primary, which is great for OEMs if they need the flexibility. Probably the toughest thing for people to recognize with CTs is what's called polarity. And here's a dot that you'll always see on the CT, and you're supposed to have the current go into the dot. This really comes in play when I get into metering, and if I've got time, I'll show you some phasor diagrams and how to read them and what you'll see. A lot of times I've seen it, they get 2 of them right, but one of them's going the wrong way because they mounted the CT wrong way. But in theory, if they've got the current going into the dot, then the current should be coming out of the dot of the secondary. In the US, we typically label this H1 for the high side. IEEE label it P1. We typically label the secondary X1, and in Europe they label it S1. So if you got the current going into the dot, it comes out of the dot on the secondary. So what happens if I have the current going backwards? Well, if the current's going into the CT backwards, then it's going to come out of the CT backwards. So you need to be aware of that. With electromechanical meters, it wasn't a big deal. With the new digital electronic meters, it is a big deal. So here's an example of a generator. And a lot of people don't realize it until I show it to them. But if you notice, there's little dots. See the dots? That's telling you where these dots are supposed to be oriented. So does anybody know? So there's no dot on the other side of the CT. That is correct, Spencer. Carlin, if you see somebody ask a question and I miss it, go ahead and read it out to me, if you don't mind. So let's look at this generator here. What did they do with the dots on the generator? This dot's facing away from the generator, and this dot's facing away from the generator. So what should those two, if you add them together, end up being? Somebody want to answer that? 0. Very good, Mark. And so we use that as what's called differential protection. We want those two to add up to 0. What's nice is this set of CT can still also be used, because I'm not summing it or adding it to this one, to give me what the current out of this generator is. And here's the PT connection. The other thing that a lot of people don't realize is, how do you determine if I don't have a dot on the CT or I can't find it, do you know how you can actually check it? If you actually take an analog meter with a DC battery, inject current through it, you'll see the needle peg one way or the other. So that's a way you can actually, a poor man's way of seeing which way the current's flowing. I want to talk about zero sequence real quickly here, because it's the only good place I had to have it, to put this slide in. When we get into protective relays, there's 2 types of connections you can make. The best kind of connection is a zero sequence CT. So in this case, this CT goes around all 3 conductors. Does a PT consume some small level of current? Yeah, but it's negligible because you've got resistance. So there is a slight loss in that. Okay, if I've got a CT that goes around all three phases, the current's going out and the current's coming back, what should this sum be? Somebody want to tell me? 0. Very good, Chris. So we use that to see if I have part of the current going to ground. If I don't have this force CT, what you can do is I can wire the 3 CTs in what's called a residual connection and run it through the ground connection. So that's a way for me to actually read the ground current if I don't have it. Now, are these equivalent in accuracy? Which is better, 0 sequence or ground CT? Somebody want to tell me? 0 sequence. Very good, Chris. You've been listening to me. Chris is one of my guys that works with me. The reason for that is we lose some accuracy in these CTs. So by having the 1 CT overall, we don't lose any of that accuracy. Now, one side note, when you're doing protective relays, you'll find that they have a neutral parameter you can set and a 0 current parameter you can set. And what we do is we measure the ground and calculate the neutral, is how it's done in a relay. So even in a protective relay, if I've only got these 3 and I need neutral, I could actually measure it through these 3 CTs and I don't have to go through the residual connection, just for your information. Okay, what's your application? If your metering is, there's 2 types of CTs you need to be aware of. There's protection CTs and metering CTs. And the question is, when do I use which? Well, with metering CTs, do I care about short circuit? No. With a protective CT, I better be concerned with short circuit. So the way they design them, a metering CT is a less expensive CT, and it may go 2-4 times full load current, where a protection CT, by definition, has to be able to handle 20 times current with no more than a 10% error. Okay? So that's the 2 types of CTs we're going to talk about today. Next thing is rating factor. So when I get into a metering CT, I start getting concerned, well, how much can I overload that CT without it burning up? And so that's the maximum continuous current you can carry. So you'll see commonly rating factors of 1, 2, or 4. And I'll actually show you what those look like. When you go to size it, this rating factor, in the spec sheets from the manufacturer, they'll actually give it to you on the data sheet. So this is a metering CT sheet. So like this 50-4, this one actually has a protection class rating and a metering. So you'll see that a lot of times. This is a 143 series. And this is different metering classes that we'll get into and what the accuracy is of those. And look, they also give you the secondary winding resistance. So you actually get how much resistance is in the winding if you need, when we go to do the calculations. So back to rating factor. So this CT right here has a rating factor of 4 because I can actually have up to 400 times current on it. So if it was 100 to 5, I could put 400 amps to this CT and I don't lose any accuracy. And it's designed that to be continuous. Okay, let's talk about short time thermal current ratings, because a lot of times you may have to overload that CT and it's only rated, or you have temperature you need to look at. So here's a formula where I can take a CT with a rating factor of 4 at 30 degrees, but I'm going to operate it at 55 degrees. Using this formula, it actually derates to 2.95, or approximately 3 times. So that's something you can be aware of. Secondary current is not rated secondary current. The difference is known as the accuracy. So even though we put 5 amps in the CT secondary or in the primary, we're not going to get exactly that out of the secondary. So there is a little, and so if we get into revenue grade stuff, you need to do more accurate CT. For the metering, a lot of us do in it's just not as critical. And you pay more for a more accurate CT. So here's the different classes. High accuracy is 0.15. You'll see a lot of utilities use that. Revenue is 0.3. And it doesn't help if I've got a revenue grade CT, but my meter's not revenue grade. So you need both of them revenue grade. Indicating is 0.6 or 1.2. So that's the different classes you'll get into CTs. Okay. All right. The next thing I want to talk about is burden on a metering CT. That consists of several things: the load, devices, the wire, and it's expressed in ohms. So you'll get into different what they call B, which stands for burden ratings. So B 0.1 can have 100.1 amps, 1 ohm, excuse me, of burden. 1.8 can be 1.8 ohms. So that's what you've got on that. And here's the different burden classes. And this is the ohms that are associated with it. And one thing a lot of times, and you'll see this in a future slide, but the manufacturers give you a rating that's rated in VA. But you really need to know what the ohms is. What happens is, if I know, we assume 5 amps coming out of the secondary, V is IR, and I is the same as A, so it's really I squared R. So if I take 5 amps squared is 25, so 22 over 25 is about 0.9. So that's how you actually calculate it. When you actually see it, you'll see it shown this way. So this is a 3% metering CT that's got 0.9 ohms burden. And hopefully you'll see that works out the same way. So here's my 0.9 ohms burden. Okay. So the accuracy and the burden, that's where we get those ratings. And everything's stated at 100% current. At 10% rated current, we get twice the error, which I'll show you in a second, which I'll show you right now. One thing that's interesting is you have a CT that's 0.3. Well, if I've got a meter application and I size it to 100%, what happens if I'm less than 100%? By the IEEE 5713 standard, I'm allowed to have that accuracy at 0.6. So we sit there on metering applications. The first thing I do is get a revenue grade meter, but I'm only operating it at 50% current. And all of a sudden, I'm not even that accurate. Okay. The reality is, here's what your actual performance is. As I get close to that 100%, I'm actually getting very close to being in the range. And you can see even the 3% is much more accurate than what the standards require. I've actually got some customers, and what they'll do, I think I've got this on the next slide. Yeah. They'll actually take and this is utilities. If I've got 100 to 5, but I know I'm only going to see typically 50 to 75 amps, because I've got a rating factor, say, of 4, they'll, instead of using 100 to 5 CT, you'll use a 50 to 5 CT. So now they're right here. So they get into the accuracy range, and then they've just basically decreased the rating factor slightly. GE ITI actually came out with a thing called an Encompass CT and kind of took advantage of that. So now what we do in the Encompass series is we stretch the rating factor. So now instead of being at 1.0 and going into the 3% accuracy, we actually can get it down to about 40%. And these CTs have a really nice wide range, so that's just a little food for thought for you. When they go to do it, here's what's called a parallelogram. This one's actually, did I lose my slide? Oh, I guess I took it out. First slide I actually used to have showed one out of the range. This 10% was up here, and this 100% was in here. The 3% and the 6%. But I just ended up cutting one slide out and just showing you when everything's good. And the burden must be specified. Okay, are there any questions? So you should size CTs based on anticipated load you will see. It's one of the questions that's Spencer asked me. It depends on the application, and I'll get into that more. Spencer, you're mainly dealing with protection CTs, and we get into a thing called saturation, and from that, I'd rather have a higher ratio, so I eliminate saturation. For metering, if metering's real critical, yes. A metering CT I could actually do lower it if I have a rating factor on it. So yeah, you got to look at your application. Okay. All right. Any other questions on metering CTs? All right, let's talk about protection CTs. With protection CTs, they'll either have a C or a T in front of it. Can somebody tell me what the C and the T stand for? Any ideas? Nobody's popping up an answer. C stands for calculated, T stands for tested. What's the 100 stand for? Any idea? Stands for the voltage that CT can produce. And I'll talk more about that in a second. So relay class C or T identifies the minimum secondary terminal volts at 20 times rated current without exceeding the 10% ratio area into a maximum specified burden. Okay? So now that I've got everybody confused, let's look at it. So here's my accuracy. Is typically on protection CTs, they've got a 10% accuracy. C in this case means it was calculated. And 400 tells me this CT at 20 times current can produce 400 volts. Okay, so if we're the IEC, they use a little different nomenclature. So they go by VA, but we know that VA was A squared R, so that's 25 divided by, so 25 VA is 1 ohm. Accuracy was the 10%, and then they actually put a P, and you'll see a P20, which is a 20 times CT, this CT's design. I've seen a lot of Europeans that are only a C10, so they actually can only, are designed to handle 10 times the overload current. Yes, Michael's calculated versus tested. Okay, so here's our first example. So I've got a C or a T100. So we know this CT can produce 100 volts between X1 and X2 at 100 amps secondary current, which is 20 times 5. All right, so if I have 100 volts, and we know we've got 100 amps, by Ohm's law, we can have 1 ohm burden. So we've got to make sure between the leads of our wire and our devices, we don't have over 100 amps or 1 ohm resistance. Here's an example with C200. Same exact example, I still got 100 amps. Now I'm producing 200 volts, so I can have 2 ohms of burden. And here's what they call, they go by B, 1, 2, 4, and 8. The highest CT you'll ever see is a B8, okay? Or a B8, it's a C800 or a T800. And that can produce 8 ohms of resistance, the 200 VA, at a power factor of 0.5. Okay, this is the most confusing slide of the whole presentation. If you understand this slide, you're an expert on CTs and PTs. What we're showing here, on the vertical axis, I show the voltage, excitation voltage. So that's how much voltage I can produce across the secondary terminals. And here they have the secondary excitation RMS amps, which is very confusing and not what you really want to see, but it's what they give you. Right here, this 10 amps here, that represents my ratio error. So right here, at this point right here, is what that's equivalent to the 20 times current. So this CT, as you can see right here, can anybody tell me how many volts that is right there? No guesses? You'd guess about 200. It's actually good guess on, guys. It's actually at 10 times excitation. You can read over here, it's 209.31. Had to throw one trick at you. So this CT is actually, and this is a 780 series, we actually call this a C100. Even though the CT can produce 200 volts, we only rate it at 100 volts. Okay, so a lot of times the manufacturers are very conservative in their ratings. This point right here is called the knee point, and that's the point at when I get 10%, or excuse me, 50% more excitation. I only get a 10% change in voltage. So that's called the knee point. That's when I'm starting to get towards the saturation and the curve flattens out. So ideally, you want to operate in this ratio down here, because now I'm going to get a real good ratio there. Okay. This is actually the Veblen equivalent of the current. So what happens is we actually lose that 10% current right here in the magnetization. So what can happen is out here on the terminal voltage, because of that 10%, you can see anywhere from 4.5 to 5.5 amps on the secondary because of the way protection CTs are designed. The reality is, as I mentioned, most have a metering CT, so we usually have a much better accuracy than even what the standards require. So how do we calculate this burden of the device and burden of the leads? So the calculation is the total burden, which is CT, is going to be my secondary resistance, called DCR, which is the DC resistance, plus the resistance of the wire and the device. Okay. If we look at wire, the rule of thumb a lot of us use is 10 gauge wire is good for what? 1 ohm per 1,000 feet. A 12 gauge wire is about 1.6 because we want to be conservative on this. And 14 is about 2.5. Okay. So that's just rules of thumb for you. Now, when you go to look at the protective relay, what do they tell me? They told me the burden's 0.2 VA. I don't want VA, I want ohms. So how do I get from VA to ohms? The way I do it is, I know that it's just I squared R, 0.2 divided by R, and we assume the I is 25. So the new protective relays have 0.008 ohms approximately. Super, super low, which makes it great because I don't have to worry. With electromechanical relays, it was a real factor. And a lot of the utilities specify like C800. The reality is with the new protective relays, you could go much lower and use a C400 or maybe a C200, depending on how much my lead wire length is, and still be fine. So let's do our first example. I'm taking 100 to 5 CT. My DCR is 0.062 ohms. My resistance of the cable was 0.1 ohm. My relay was 0.02 ohms. Total is 0.182 ohms. So if this is 100 to 5 CT and I see 20 times that, which would be 2,000 amps, and my ratio is 100 to 1, we'll produce 100 volts. So across that, I've only got a burden of 18.2 volts. Okay, so we just need to select a CT with this knee point above 18.2 amps. So I could easily go with a C50 on this application and be perfectly fine. A C10 is not going to work. A C20 is very marginal. Okay. Next example I've got. A 780-102 is 1,000 to 5 CT, and it's a C100, so we know it can produce 100 volts. Well, the question is, can I use that for my application? If I add all these resistance up, I have 4.28 ohms. Once again, 20 times that's 20,000 amps. So therefore, I'm going to produce 42 volts. So prevent CT, so I've got a knee point above 42, I'm great. What happens if all of a sudden I see 40,000 amps go through that CT? Well, this is going to be at 84.85 volts. I still should not saturate that CT. If I got to like 60,000 amps, now I'm going to start to saturate it because I can't produce enough voltage to get through the burden. Other factors that affect it: frequency. Low frequency, high accuracy are not friends. One of my takeaways is you can't use 60 hertz CTs on 50 hertz applications. You can use a lot of 50 hertz CTs on 60 hertz applications because it's going higher in frequency. Low current ratios, high accuracies don't work well either. You'll see when we look at CTs, the voltage they produce and everything on low CTs is much worse. And high burden, high accuracy are not friends. The higher that burden goes, the worse it gets. Okay, I want to talk about what's CT saturation. A lot of people get mystified by that. So what I recommend you do, and we've got a copy of this on our website, and if I grab the right slide, it's going to be the next one. Yep. Okay. So this is the Power System Relay Committee, the PSRC, came up with a CT saturation calculator. And what you can do is put in all your parameters and determine if this CT is going to saturate or not. So let me show you what I've got here. This blue line is the ideal sine wave. Okay. This black line is the CT saturation line. And what's interesting is the first cycle doesn't even saturate as bad as the second cycle. The next thing I'm going to show you is this is a Fourier transformation of that primary waveform. So this blue line. So the relay manufacturers actually do that to get their calculation of if the relay will work. And this is the Fourier transformation of the saturated waveform. Okay. So that's what you got there. You also have this. Can anybody tell me why this started off this way and then finally balanced out around the zero axis? Does anybody know what that's called?
DC decayed.
That's right. It's the DC offset. Very good, Spencer. And you got to take that into account. That's caused by magnetization when they stop the CTs. And, you know, CT is just magnet and wire. So you can end up with some residual magnetism. If you want a copy of this, I'm on our website, www.l-3.com. You can go to the menu, go to resources, and I've got a section called Transformer Power Current and Potential. Here's the presentation that'll be on there later today. And I'm also going to try and put this video. And here's the CT saturation calculator, and they have a cheat sheet telling you how to set it up. So I've actually got that on my website if you want a copy of it. Okay. Factors that affect saturation. The DC offset, I talked about that. The fault magnitude, you know, 100 to 5 CT at 20 times is 2,000 amps. Well, all of a sudden I've got a situation where my AIC rating, amps interrupting capacity, you know, is coming in at 50,000 amps or 20,000. You know, 20,000, now I'm at 200 times CT. That CT is going to saturate. So Spencer, getting back to your application, with protection, higher ratio CTs are actually better for protection. For metering, you're better off with low. The turns ratio, the higher the ratio, the less likely it's going to saturate quicker. The secondary burden we've talked about, the CT accuracy, and remnants flux, which is left in there. That's if the core interrupts when core is saturated. DC fly into the windings, need a voltage above 60% of knee point to reduce the remnants to less than 10% of saturation. Unfortunately, you know, a lot of times you'll hear somebody say, I demagnetize the CT for remnants flux. Problem is, next time that thing is energized, depending on where it kills, the current cuts off in the cycle, you may just put it right back. Tips for avoiding CT saturation: use higher ratios, use a separate setter for higher ratios for high fault currents, reduce the secondary burden, you know, use step down auxiliary CTs, which I don't personally care for. I've covered that really quick. Are there any questions on CTs? Okay, let's go into potential transformers. So potential transformers, a voltage transformer just changes the voltage from the primary to the secondary. Secondary on PTs are usually 115 or 120 volts. A lot of times people confuse what a voltage transformer is than a current power transformer, a CPT. The difference is Current power transformers are designed for contactors, relays, and devices with high inrush current. A lot of people don't realize it, but a solenoid is like a 0.5 power factor, and they give you the rating in watts. Well, all of a sudden, when I go to VA, which is the way I size transformers, the VA is double what the watts is at 0.5. So it's a real, you need to be cognizant of that. A control power transformer will not maintain the regulation that a voltage transformer will. A CPT, you may see the voltage drop 20% during that inrush, where a PT will not do that. Here's a picture of just a 5 kV PT. Control, not current. I'm not sure what you're asking me on that question, Michael. Here's a PT right here. 5 kV. This one came with primary fuses, and this is the secondary terminals right there. And it's just a simple ratio. Now, this works better than a CT. If somebody tells me the ratio is 35 to 1, then I know it's a 42 to 120. I just make the assumption it's 120. I don't have that issue like I did on CTs, where they may be talking European ratings or US standards. Now, do I need to, am I okay using a 35 to 1 PT? Okay. Am I okay using a 4200 on a 4160 volt system? The answer is yes, because what's going to happen is I've got this ratio that I put into the multi-lin relay. Well, if it's only seeing 35, it's going to keep that ratio. So what will happen is I put in 4160, I'm going to get 119.2 or whatever volts out. And I know that's equivalent to 4160 because I set the ratio up. So the beauty of the multi-lin relays is it's going to automatically compensate for us and tell us what we need to know. There are VT accuracies ratings on VTs, 0.3, 0.6, 1.2, and 0.15. And they're all done by IEEE 5713. They're designed to handle for between 90 and 110% rated voltage. So that's the range they've got to work in. One thing I've always found interesting is when my customers that buy metering VTs, they'll specify it. They don't just say, give me a W. They may say WX and Z. So a lot of times they have 3 or 4 ratings on the CTs and the VTs, and the VTs are rated for that. Okay, and they're all designed at 60 hertz. So here's one. It was 0.3, and they wanted WX and Y, or you may see 0.6Z, 1.2. Okay. Just like I had the parallelogram for the CTs, if somebody wants to know, here's what the estimation, the accuracy for voltage transformers. And a lot of that depends on the power factor. So that's how that's set up. And here's the different burdens and how they're rated. VT installation. You don't want to operate a VT over 110%. You need to be careful in whether it's line to ground rated or line to line. So let me ask you a question here. If I've got a PT that's got 2 bushings on it, is that rated for line to line or line to ground?
Line to line.
Line to line, that's correct. If I have only 1 bushing, then I'm assuming the other side's connected to ground. So if you see, Michael, line to ground. If I have 1 bushing, you're correct. It's line to ground. Okay. Now, on an ungrounded system, which we're the post-Clover rep, so I also do a lot with that. You need to make sure those VTs are all rated line to line, because if I have a ground, one face goes to ground, the other 2 go up by the square root of 3 to line to line. So I may have to use a PT that's line to line. I've got a neutral grounding system in place, but because I've got the ratio, I'm still okay, because the relay can automatically compensate it. Okay. Here's the different configurations. sometimes you'll actually see, they'll say, I want group 3 or group 2 with 2 bushings. You know, here's this one bushing. It's VT group 3, it had to be a Y connection. You know, here's an open delta, so it had 2 bushings. So this is some of the different configurations, and you'll see these different VT ratings and codes. A lot of people, you may have an open delta configuration, okay? So an open delta, a lot of this is seen in industrials because they don't want to buy the third PT. Personally, I like to have the Y configuration because I get the third PT. In this case, I actually was looking at a customer and he had B phase go to ground. Well, I couldn't see the voltage on B phase because it was automatically grounded. You know, so you don't get as nice a reading on the oscillography. There's some other times that you need it too when I get into some other applications. So required information for specifying CTs and PTs. You need to know the voltage, the frequency, the power frequency, kV, I shouldn't say frequency, VAL level, and if you need any of the specs, is it metering and protection? You know, we need to know the dimensions. I need to know the outside dimensions and inside. People say, give me 105 CT, and I'm going, you know, and I give them one, and it's always wrong because they say it doesn't fit, or it's wrong, the window's not big enough. You know, do you want rectangle, you want circular, and the ratios. Do you want bar CT? So that's some of the requirements for that. Is it indication? Is it metering, protection, frequency, rating factor? We talked about that. Insulation class. On PTs, here's some of the specs for that. Same basic requirements. Thermal rating, 1 bushing, 2 bushing, secondary voltages. You know, fusing, do we need that? So here's some take-home rules. I never want to open circuit a CT, okay? Because the CT, I've got current going through the primary, wants current going through the secondary. If that current has nowhere to go, it drives the voltage up. So never, ever open circuit a CT, okay? You never want to short circuit a VT. That's no different than taking the 120 volts coming out of a wall socket and touching the 2 leads together. They're going to short out. So you never want to short out a VT. Metering applications do not require a C-class CT. C tells me it's for protection, okay? CT secondary leads must be added to CT burden. We've talked about that. In fact, that's probably the biggest factor with new protective relays being so low. I never want to use a 60 hertz rated VT on a 50 hertz system. It tends to saturate at lower frequencies, get excessive temperature. All kind of bad things can happen. Exercise caution when connecting grounded VTs to ungrounded systems. We talked about that. I had a case with City of Atlanta they had a solidly grounded system. They converted it to high resistance, and all the arresters blew up, the VTs blew up because everything was designed wrong. Because they had, you know, 3,000 volt arresters instead of 5 kV. We also have arresters if you need that. Rule 7 with GE. It's common practice to apply 600 volt CTs to system with higher voltages. The reason you can do that is because you have fully insulated conductors going through the window. So as long as you don't have a bare wire, you can use a 600 volt CT on a 5 kV application. And I'll show you some slides of that, how the manufacturers do that on Switchgear, if I've got time. The last take-home rule I wanted to show, if you're using a shield, you need to make sure on a ground CT that I run that shield back out, because otherwise the current is going right back out, and it negates the CT from seeing the proper. So just be aware of that. Okay, are there any questions at this point? Somebody wants a class on test switches, purpose and configuration. That's a good idea. Thank you. All right. So let's talk about the selection process, and here's some different CTs. So you need to know the function, type of equipment, specific requirements, and how you select a CT. Is it indicating or is it protection? So, metering CTs are less weight, less space, less cost. Protection CTs are bigger, heavier, cost more. If I've got something like a low voltage switchboard, typical CT is something that looks like this, the 5 series of 19R or the 8 SHT. The problem with this CT is it only may be like a C10. These are very economical CTs. So if I've got to run 500 feet, I'm not going to have the voltage I need because of the burden, and this could be a real problem. And all the switchgear manufacturers are going to give you the cheapest CT they can. So you may actually want to specify that when you're doing this. VTs, some of the typical models I'll see in a switchboard is the 460 is probably the most common. 3VT 460 is just a 3-phase version of that single-phase CT. So all 3 VTs. So if you want to measure accurately, you could do that. Motor control centers, here's some of the CTs that are used. Here's one that's a 3 CTs in 1 that I've seen used. Switchboards, now you're going to want a better class CT because now I need to make sure on instantaneous I'm going to trip these breakers out. Here's a low voltage switchboard. I don't know how well you can see this picture, but I've got one CT on the primary because they actually were too big to put all 3. They put 1 on the primary, 2 on the secondary. But the current going through here should be the current going through there. This is a 2000 amp. They used a 560 or 561. Sometimes they'll put 2 or 3 sets of CTs if you've got different applications, and they should all fit on there. Here's a better picture of it. This one, they could have put them all on the same side. Okay, this is a 4000 amp. Using a 562 or 563 is what they went with. So that's what the cell looks like. Low voltage switchgear, no room in front. Here's one actually on the bus bars. What's interesting, look what the manufacturer did. They come with the CT shorted out. Why is that? Because we know we never want to open circuit a CT. If I get into the 5 kV CTs, there's a little jumper strap that comes on them as standard. So if the CTs weren't, if the metering wasn't pre-installed, you'll see this. Here's a typical VT installation.
You have several questions, Sean.
Oh, I do? Okay. Switchgear. 0 volt level, they're using 600 volt CT and XKV wiring is limited to. Yeah, typically it's 35 kV. I don't typically see a 600 volt CT above 35 kV. And I've actually got a white paper I can send you on that, where ITI actually says you can use the CTs on it. But 35 kV is really the cutoff. Can saturation of a CT occur from nearby conductors? No, I wouldn't think nearby conductors would be able to have any influence on your CT. Back in the slide with the staggered CTs. Spencer, what do you want on the staggered CTs?
You can stack them.
Can you stack the CTs? Yeah, I could put another CT. Depending on how much the depth of this bus bar, and depending on the manufacturer, you may be able to put 2 or 3 CTs on there. Yeah. I'll show you another slide if I've got time of a CT. In medium voltage switchgear, I tend to go with a 680. That's probably the most popular CT. The 778 is the same CT, but it's a higher accuracy, so it's about twice as thick. So I may or may not be able to fit all those on the bus bar. Yeah, here's one where you can see you'd have room. Because see, the bus bar goes in here, so my female stab is going to be all inside here, so I should have room to put a couple sets of CTs. stack them on this. Yeah, so here's a good application where I could stack the CTs. See how the 780 is much thicker, 785, I guess, versus the 780. So, you know, that's all a factor. And you just got to talk to the manufacturer if it'll fit. But yes, you could stack them. Here's a model 203 that was actually put in some medium voltage switchgear. You know, here's a ground fault CT. So, this is a zero sequence CT, right? Because it's going around all three conductors. So is this better than a residual connection?
Yes.
Yes, absolutely. Because I don't have to worry about that 10% error. The PTs, a lot of times you'll see them in what they call a PT drawer. Sometimes I'll have two, sometimes three. So you can actually open these drawers, pull out the PTs, and these stab on. Okay, so that's a great way, because you need to be able to get to those so I can get to these fuses if they blow. So there's the rollout drawer, installed in enclosure, withdrawn from enclosure. So this is a CPT. They also put in one of the drawers. So one of these had the PTs, one had the CPT. And this one was like a 15 kVA. Here's a motor control center. It's got a multi-lin 369 on there. Nice. So here they mounted the CTs in the, you know, and they typically use the 112 to 117. This is a really nice quality CT I've seen in a lot of applications. And this is one of my go-to CTs. It's like the 114. Here's the generator. Okay, it's the largest CPT you can fit in a switchgear. Spencer, I do not know what the largest CPT you can fit in a switchgear lineup is. Good question. Okay, so this is on a generator. Can you tell me if it's on the line side or the ground side
Ground.
of the generator? Ground is correct. How did he know that? Because all three of these are tied together. If I went all the way back to that other CT, you'd see they were all tied together. So this is the ground side of the generator. Excellent. Good job, whoever answered that. You'll see station class CTs. So actually, you know, I said 35 kV. This is actually a 600 volt CT that the switchgear manufacturers that make, like GE Hitachi right here in Atlanta, or Arriva, which is the GE, they're actually using 600 volt CTs, and this is on a 69 or 72 or 128 or 250 kV system. But they're doing it, you know, they've got huge insulation levels because of these, the insulators. So here's an application that I could have a 600 volt CT on a 240 or 250 kVA. In switchgear, I typically don't see it over 35 kVA. Here's a pushing CT station class. So that actually goes in this housing right there. Flip over current transformers, you know, sometimes they'll mount them over. B07s are real popular for retrofits. Here I'm showing some DTs and some CTs. This is a 5 kV application. Here they went with a bar type CT. You know, if you want to save money and you've got the insulation, you could use a 600 volt CT. Here's an air terminal chamber where they mounted those. Okay, now the fun part. All right, so here's an example. And what I've got here, the longer line is VA, here's VC, here's VB. For 20 points, who can tell me, is this ABC rotation or ACB rotation? While y'all are thinking about it, I'm going to answer this question. I personally don't like split core CTs because you're breaking the connection on the iron core and it does not give you as good an accuracy.
ABC.
Somebody said ABC. I want somebody else to say ACB, just so we're going to have an argument. ACNB, okay. Who threw Brandon, there's no neutral on this one. Okay, this is actually ACB. The rotation is always counterclockwise. And what you want to do is pretend, hopefully I don't screw up this with the spotlight. You want to pretend you're standing right there at 0. So as this is rotating around and I'm standing right here, first I'm going to see VA, then I'll see VC, then I'll see VB. Does that make sense to you? So it's ACB rotation on this one. And what do I expect?
On a GE generator, you're right.
Well, yeah, but I'm just, a lot of times customers make these connections wrong. Alabama and Georgia, one of them's ACB, one's ABC, or ACB and ABC. One of them's backwards from the other. So one state's always wrong. But so this is an ACB rotation in this case.
Okay.
And what do I expect the current to do? Do I expect the current to lead or lag the voltage?
Lag.
I expect to lag, absolutely. And in this case, if I'm standing here and my rotation's counterclockwise, this current is lagging this voltage. So this is actually the proper way that should be done, okay? Get back to my drawing tool, come on. Uh-oh. Come on, let me back. Oh, come on. Oh, hang on a second. There it goes. Okay. So let's go to the next slide. So let's look at this one. Right here, the graph 1, Phasors set is my current. So these are my currents, and these are my voltage. If you look at this, this current actually looks like it's leading the voltage. So I'd say that's a real problem if it's supposed to be lagging. But what happens is, what am I giving you here? I didn't give you VA. This is VAB. So if I look at VAB, what's it made up of? VA minus VB. So the VA is really going right here. So the first time this customer called me up and said, hey, I'm showing the current leading, not lagging, I said, no, it's okay. And the reason was because the VA is really right here, and then the voltage is lagging it, or the current's lagging the voltage.
Excuse me.
Okay? So that was your first test. So here's your second test. Okay. In this case, I'm going to give you a clue. Something's wrong. The small arrows are my voltages. So here I'm seeing VAN. It's right there. Here's B. Here's C voltage. So I know this is ABC rotation. I would expect A phase current to be right here. B phase current, I expect to be right there, which it is. Or excuse me, B phase current to lag the voltage, which it is. So B phase is good. But A phase voltage is seeing C phase current, and C phase voltage is seeing A phase current. What do I do, guys? Somebody want to answer? How do I fix this?
A and C phase are backwards. Swap them.
That is correct. That's correct, because you know, because you've done it 1,000 times. That was Billy Sanders for those who didn't know it. That's correct. A and C phase are backwards, so you got to physically put the wires going to A and this one's going to C to A and A to C. If I saw this going this direction, 180 degrees backwards, what's that tell me? My dot orientation's wrong. There turns out, guys, there's like 32 different combinations that I've come up with. So you've got to look at this phasor diagram to figure out what's the right answer. Trying to guess and swap A and B, because you may have A current with C voltage. I mean, it's a mess. So any questions at this point? Okay. Real quickly, I guess that's it. That's it. That concluded it. Yep. Okay. Perfect. Right on time. Anybody got any questions? You can unmute yourself and ask if you want. or you can email me. It's in the chat. Questions?
Hey, John, this is Billy.
Yes.
I wanted
I
to
know.
let everybody know, I put it in the chat, but I do have this uploaded to the website. So if you go to www.l-3.com and go into the menu and resources, like John already said, John, if you want to show them right there real quick.
Yeah, I will.
It's under transformers, power, current, and potential. And you can download this presentation and use it.
I gotta slide this over. Okay. Well, let me just do it this way. I've got it. Well, here's the lane. Okay, there we go. Okay, so this is our home page. If you click on menu, resources, here's a bunch of great resources we've got. If you need the ANSI symbols, there's all the ANSI symbols. I teach classes on communications. That's some of those. Under transformer power, here's the CT/PT presentation. So you can download it right there. And there was the CT calculator. Here's stuff on digital relays, generators, meters. So there's stuff on power quality and meters. Motors we've got, neutral grounding, other transformer white papers. My favorite is in others. If anybody's got kids and you got to teach them how to drive, I recommend you grab Levine's driving requirements and make your kids do everything on there. Okay. Any other questions? Minus the N, yes. Typo. ACB, good. Thanks, John. Got to go to another meeting. Yes, should be anti-clockwise. Lag, got ANC swapped. Yep. Incorrect connected VCTs. Concur with driving requirements. Yes, Spencer, I understand. All right, guys. Thank you very much. Be safe out there.
Thank you, John. Thanks.